out there, but the ones with the disks around them, the pictures I showed from the Hubble Space Telescope, those are going to be T Tauri stars someday. T Tauri stars are after the disk goes away. They're still young and they have some signs of activity. Variable. Yeah.
Should I try again?
Yeah, sure.
Really no, I just want to make sure you're okay.
I'm fine.
If in one of those areas you have like several stars forming, and I was thinking the same thing about when the star finally ignites, like the very first one, does it affect the other stars where it can actually prevent them from completing their formation?
Well, that's a great question, and the answer is we don't know. There's actually the idea that one star, particularly the massive stars, which have these big winds, they can blow bubbles of gas into the interstellar medium. They can actually compress material, and that could lead other clumps of gas to collapse. So in fact, it may stimulate star formation rather than prevent it. But it's certainly nearby a young forming O star, a big star. The environment is so harsh with the winds coming off the star and the radiation coming off the star, it will just blast to bits anything near it. So that will prevent local star formation, but may stimulate star formation further out. Yeah.
There's one comment about there was a question: how did the original small clusters start? I mean, small clusters of atoms start together. You said you needed the inside of a supernova to get that to happen.
All right. So the heavy elements are made inside of stars, and they are dispersed by supernova. That's the only way you can get these heavy. Anything heavier than helium, say.
Yeah, right.
That's the only way you can get it out into space.
Right.
Then from those elements, so that becomes mixed in with the gas, and new stars form. And when they form, then these heavy elements can then do their thing. Now, the intermediate step is the formation of dust grains. So the first dust grains presumably form inside the atmospheres of red supergiants.
And the problem is cosmology, is if you've got a homogeneous universe, how do you get that first cluster to start?
That's a great question, and so certainly the heavy elements can come from the first stars, and then the new stars can
How do you get the first star?
The first star will be not too dissimilar from stars now. They will have slightly different properties, but once you start mixing in the heavy elements, then all is well. So the first stars made the heavy elements, and then things proceed at a pace.
Your studies are primarily with really heavy stars, massive stars.
Right.
Where does Eta, I can't even say the word, Carina?
Oh, Carina, yeah, that's like the...
Where does that fit into this?
That's like probably the most massive star, at least the most massive nearby star that's known. So this presumably was in one of these infrared dark clouds, say 100,000 years ago, and was broken out. In fact, you can see all this molecular material around Eta Carina. It's sculpting the molecular environment. It's carving out this huge bubble, and you see all these filaments and knots that it itself is creating, and it is highly variable. So there's presumably gas nearby that it's still continuing to create and accumulate.
Its distance from us is?
Oh, I don't know the exact number, but not more than 1,000 parsecs. A few hundred parsecs, I believe.
Did I hear you say the interstellar dust particles are as big as smoke particles?
Typically, yeah.
That's big.
Well, I mean, of course, there's no one size.
Yeah.
So they span a range of sizes, but cigarette smoke is close
and
these to the range of sizes.
All elements, probably. Carbon, aluminum.
Oh, yeah. So the dust grains themselves are formed out of carbon, oxygen, silicon. Those are the primary elements. And they follow the cosmic abundance. Those are the most abundant elements in local space.
Stupid question time. I'm sorry.
That's my privilege.
Why didn't the asteroid belt continue to accrete?
Oh, that's a great question. And presumably, it's because Jupiter was so big, it prevented a planet from forming there. The gravitational influence of Jupiter just broke up anything that tried to form.
Now, is there some diminishing return point that when a star starts to become stable and starts radiating light, what does that do to the disk where the planets are forming? And does the disk have to get some big things in it before the star produces too much radiation?
That's an interesting question. So one of the problems that we have with the newest discoveries about planet formation, or discoveries of new planets, the current theory suggests that the big planets have to form far from the sun because that's where ices are abundant. And you have to make the big planets out of really abundant material. And finding these big planets, like bigger than Jupiter, very close to their parent star, throws that theory on its head. Right. So but this bears on your question. So one idea is that the planets form far out and they move in. And one of the ways they move in is that the wind from stars clears out the material on the inside that would prevent them from coming in. So it's ejecting some things. And when something is ejected, by conservation momentum, something else has to come closer.
So that could be something involved in calculating how long it takes for a star to turn itself on?
Yes, exactly.
They have to be long enough so it doesn't blow everything away that would form planets.
Well, you know, the star doesn't care about the planets.
Right.
I mean, that would be the formation, the timescale of the formation of the solar system. But, you know, whether or not Jupiter exists, the sun doesn't care, right? And no star would care whether or not a planet is formed. But if you want, if the observations that solar systems are very common, then this process has to be universal, and the disks and planets have to be long enough lived to survive.
But then that throws in the magnetic effects, the electromagnetic effects, because the star should be rotating faster than everything else in the solar system.
Right. So that's an angular momentum problem, right? The ice skater pulls her arms in. She's the fastest spinning, but most of the angular momentum in the solar system is in the planets, not in the sun. So how that happened? It had to break somehow. That angular momentum either had to be transferred or expelled from the sun. And the current, as you suggest, the current idea is that the magnetic fields have a role in that removal of the angular momentum from the sun, or from any star.
Okay, one more question.
In our solar system, we have, our sun has a lot of hydrogen, helium. These clouds that you described seem to have a lot of other elements. Is it just that our particular sun has a lot of hydrogen, or are these clouds?
The sun is typical. So when we're talking about, I mean, most of the material in the universe is hydrogen and helium. And then the heavier elements, what astronomers call metals, are actually an insignificant fraction. They're tiny. So, for instance, in the carbon monoxide molecule that I've been looking at, there are typically one carbon monoxide molecule for every 10 to the 5 hydrogen molecules. So it's mostly hydrogen, but we can't, there's no convenient way to look at hydrogen directly, so we have to look at these tracers, these other tracers.
So the hydrogen is...
Yeah, so don't get the idea that these are clouds that are made primarily of carbon monoxide. They're not. It's a very carbon monoxide is a very minuscule component of these things.
Okay, help me thank Dr. Green.